In this video, we'll look at the second part of our goal for this section. We've seen how to solve linear differential equations that come in systems with different functions y1, y2, y3 that are some sort of intertwined. A more natural question would be to solve a differential equation in a single function y, but that differential equation could involve the second derivative of y, the first, and y itself. So this is called a quadratic differential equation, and we'll see how to solve it using this example. So I'm going to look at y double prime minus 7y prime plus 12y equals 0, and I want to solve it. I'm going to use what we've learned about systems. So the first thing I'll do is I'll rewrite this as a linear system of two different functions. So let me put this, give this a name. So rewrite dagger as a linear system. So this is not linear. I have y double prime. I'm going to use y1 equals y. And then my y2 is going to be a function that's not independent from y1, but that's okay. I'm going to use y2 equals y prime. Alright, so let's see how having this differential equation in y double prime y prime gives you a differential linear system in y1, y2. So first of all, y1 prime would be, well, y1 is y, so it's y prime, and y prime is just y2. So we would get 0 y1 plus 1 y2. So that would be my first equation. Now this equation has nothing to do with our differential equation and everything to do with my choice of y2 being the derivative of y prime. So this equation will always be the same, whatever you start with. Then the second one, I'm going to look at the derivative of y2. y2 is y prime. So I'm going to get y double prime. I'm not allowed to leave y double prime in the equation, but I don't have to because I have this equation. This differential equation tells me how to write y double prime as a linear combination of y prime and y. So here I'll have, in this case, this one depends on the actual differential equation you start with. So I'm going to get y double prime is 7y prime minus 12y. And now y is y1, so I get minus 12y1 plus 7. Y prime is y2, 7y2. And so I get a system like we had with y prime equals something y. Actually, let me write it as y1, y2, just so we're not confused between this function and the vector that we're looking at here. And the matrix is 0, 1, minus 12, 7. So now I'm going to solve this system. going to solve it using diagonalization. So my matrix A is 0, 1, minus 12, 7. So I want to diagonalize this matrix. Let me write it underneath. So PA of X pause a bit because something, maybe not something magical, but something nice happened here. If you look back at what the differential equation was, it was y double prime minus 7y prime plus 12 equals 0. So what I'll get as my eigenvalues are related to the differential equation I started with. They're kind of the zeros if I really think of it as a quadratic. So in this case, I'll get x minus 4, x minus 3. So my eigenvalues of 4 and 3. And for lambda equals 3, I'll get a minus 3I is minus 3, 1 minus 12, 4. That reduces to 1 minus a third, 0, 0. So this is S. So x, y, let me just fast forward a tiny bit, is going to be a third 1 times S, so my vector will be 1, 3. Alright, for lambda equals 4, I'll get a minus 4I, which is minus 4, 1, minus 12, 3, sorry. And so this reduces to 1 minus a fourth. I'm going to take this as S. I get xy is 1/4 1s. And so this is v of 3, v of 4 will be 1, 4. Alright, so my matrix P will be 1, 3, 1, 4, and my matrix D will be 3, 0, 0, 4. So as we did in the last problem, I'm going to solve for U. So this was step 1. Step 2, solve for U, which is P inverse Y. So U prime is du, which means that U1 is 3, prime is 3U1. Keep putting, sorry. And so U1 will be C1E3X. And then u2, this is so much better, is 4u2. And so u2, again, is c2 e to the 4x. All right, so we have u. It's c1 e to the 3x, c2 e to the 4x. And finally, we solve for y. And so y is p. Makes me laugh every time, a bit childish. All right, y is pu, so p was 1, 1, 3, 4. U was c1 e to the 3x, c2 e to the 4x. We just need to multiply it out. We'll get c1 e to the 3x plus c2 e to the 4x. 3c1 e to the 3x plus 4c2 e to the 4x. Alright, so that's the solution for the system that I created in y1, y2. But I don't really care about the system. I cared about the original differential equation. So in part D, I think, we're going to we need to find back the original y. So if you remember, we took y1 to be y and y2 to be y prime. And so in this, and you can check it right here, the second row is just a derivative of the first. If I take 3, yep, and the 4 comes down, perfect. So really, this is just a derivative of the first. That was one of the conditions we imposed on the system. The first row is our solution. So my y is c1 e to the 3x plus c2 e to the 4x. Let's double check. The original differential equation I had was y double prime minus 7y prime plus 12y equals 0. So y double prime is, well, y prime is 3c1 e to the 3x plus 4c2 e to the 4x. We knew that because it was the second row. And now y double prime is 9c1 e to the 3x plus 16c2 e to the 4x. So let's plug it into this. Y double prime minus 7y prime plus 12y would be 9c1 e to the 3x plus 16c2 e to the 4x minus 7 times this, so 21c1 e to the 3x plus, so let me put the minus with it, plus minus 28 c2 e to the 4x and plus 12, so plus 12c1 e to the 3x plus 12c2 e to the 4x Let's make sure everything canceled. 9, 12, that's 21. Yep. 16, 12, that's, yep, that gives you 0. Again, you don't need to check in the end. I just want to show you that the method I'm giving to you actually works, and you get your solution for the differential equation you started with.